One more example for class number 11. This is example 315, and we have consider, if you will, 1 kilogram of water on a table at room conditions, 20 degrees Celsius, 100 kilopascals. We want to examine the energy changes for each of these processes. What if we were to accelerate this from rest to 10 meters per second, raise it 10 meters, and then heat it up 10 degrees Celsius? What would those processes, what would be the relative changes? How much in energy? So let's go ahead and draw this thing on a table. And it's in a bucket. And it's a see-through bucket, apparently. It's not a nice bucket. And we're going to zip it up. Whee! We're going to throw it up. Whee! And then we're going to measure the temperature. Okay, so we're just doing a lot of stuff. So let's see. If we increase its velocity, we're going to accelerate it. So what we're doing is we're getting kinetic energy, which is 1/2 mv squared. Well, I want to use capital V. We use that V too much for specific. So there you go. There's a capital V. So that's 1/2 1 kilogram and 10 meters per second squared. 10 meters per second. I'm sorry, not squared. That's not accelerated. I should probably, let's go ahead and do a little units thing going on here. 1 kilogram and 10 meters per second. We're going to square them. What we're left with is 50 kilogram meters squared per second squared. Anytime you see a kilogram a meter in a second squared, you know that it's going to be a unit. It's going to be a Newton meter. It's going to be a Newton. And we know that 50 Newton meters is 50 joules. All right, so that's what happens if you accelerate it from rest. Now, what if you raise it up? Well, that's going to be potential energy. And that's going to be mg delta y. So 1 kilogram, g is 9.81 meters per second squared. So that's going to be a Newton just right there. And this y is going to be 10 meters. So you're going to go 98.10 Newton meters, which is a joule. Now we're just going to heat it up 10 degrees, right? So if we look up in table A.4, I think it's 8.4. Seems like it should be 8.5. I feel like this should be 8.5. I'm going to write that as 8.5. And if it's not, you can write me a nasty gram. I'll allow it. Give me an unlike button just to tell me you're there. Only we will know. Only you and I will know if you give me an unlike button. They don't show unlikes anymore. It's interesting, don't you think? All right, so this is just going to be the amount of internal energy that's going up. There's no real pressure work going on there, so internal energy. It says the delta U, and that's going to be CV. Well, a lot of times we like to M. We like to put the M. So the M CV delta T. So we went up 1 kilogram and 4.18, and remember that's kilojoules though, right? 10 degrees. It doesn't matter, the degrees doesn't matter for Kelvin because it's a delta. So if they were both Kelvin, you would still get the same delta out of the thing. So you would get 41.80 kilojoules, but you got to be careful. Those are kilojoules, so you want to compare them. 41,800 joules as a mean of comparison. So you can say that the temperature makes a heck of a big difference, the change in temperature, compared to changing it 10 meters per second or raising it up 10 meters. We're talking a lot of energy. in a relative manner, right? Because of the temperature changes. I don't know what the big picture is that they want you to see from that, except that these are, these are values sort of a real thing that maybe you could picture. You could picture 10 meters at 30 feet raised up, or 10 meters per second, which I think is pretty fast. Was that 30 feet per second or thereabouts? Yeah, that's pretty darn fast, right? You could picture 10 yards, right? Someone going that in 1 second. It's fast. So anyway, that's the last video for this class, and we're going to go to class 12 very soon. In fact, probably next.